Good morning students, welcome back to online classes. In the last session, we have discussed about the classification of elements into SPDF blocks based on electronic configuration and classification of elements into inert gases, representative, transition and inner transition elements based on their reactivity. Now let us discuss about a new topic called as periodicity and its trends. Periodicity. What's meant by periodicity? See, we have several properties of elements like atomic size, ionization potential, electronegativity, electron affinity, melting points, boiling points, and so many such physical properties were there. How these physical properties are varying across the periodic table, across the period, down the group, what's the trend? Whether it is going to be repeated after certain intervals, this is what we are going to study. It was noticed that at certain intervals, these properties are again getting repeated. For example, when it comes to this electronic configuration, after a gap of two elements, again hydrogen configuration, similar configuration is shown by lithium. After a gap of 8 elements, similar configuration is shown by sodium. Next, potassium, rubidium, cesium. See, such repetition of properties at certain intervals, not regular intervals, certain intervals. Repetition of properties, such repetition of properties at certain intervals. Like with respect to alkali metals, if you consider, alkali metals means first group elements like 2, 8, 8, 18, 18 and 32. This gap is with respect to alkali metals. Repetition of properties at certain intervals of 2, 8, 8, 18, 18, 32 is called as periodicity. And such properties which are getting repeated at certain intervals in this way are called as periodic properties. In fact, all other periodic properties like melting points, boiling points, densities, etc. all depends on some basic properties, namely atomic radius, ionization potential, electronegativity, etc. So for all these properties, firstly, one should be perfect in this atomic radius and its trends. So what is atomic radius? Actually, when this is the nucleus and electron density is diffused around the nucleus like this, there is no fixed physical quantity. We have studied that in atomic structure already. See, electron cloud is diffused in this way, in different styles. So atomic radius, electron density is diffused in this way, diffused around the nucleus in different variations. Now atomic radius can be defined as the distance between the center of the nucleus and the outermost electron of the diffused electron cloud. That's the final definition we can give for atomic radius. What is atomic radius? Distance between the center of the nucleus and the outermost electron of diffused electron cloud, outermost electron of diffused electron cloud. But how do we come to know that this is the outermost electron of diffused electron cloud? How to infer that? We have no specific thing, because atom is not always available in its free state. Say some atoms may be available in free state. Some atoms are, most of the atoms are available in combined state. So with respect to its state of availability, we have to define its atomic radius. For example, if it is a non-metal, always these non-metallic elements are available in covalent molecules, in the form of covalent molecules by forming a covalent bond. If it is a metal, it is available in metal crystal, in which one and other metal atoms were held by metallic bonds. Like that, with respect to its state of availability, we can define the atomic radius. So that's why with respect to that availability and state of availability and other features, atomic radius is mainly classified into 4 categories, namely covalent radius, metallic radius, covalent radius, metallic radius, van der Waals radius and ionic radius. van der Waals radius and ionic radius. So usually conventionally atomic radius means we can take either covalent or metallic radius, but we can simply call either covalent or metallic radius with the term atomic radius. But we have to apply with respect to the nature of the element. If it is a non-metal, the same atomic radius must be called as covalent radius. If it is a metal, the same thing is called as metallic radius. That depends on the nature of the element. Now, when it comes to the covalent radius definition, covalent radius, consider, suppose you consider chlorine. Chlorine is available as a Cl2 molecule where the two chlorines were held together by means of covalent bond in this way. So these two chlorines were held by a covalent bond, right? When these two chlorines were held by a covalent bond, you have to measure their internuclear distance like this, distance between their nuclei, distance between the nuclei of two covalently bonded atoms. Measure their internuclear distance. This is called as internuclear distance. And half of this internuclear distance is called as atomic radius. This half is the atomic radius of first chlorine, the other half is that of second chlorine. So what's the definition we can give for covalent radius? Half of the internuclear distance between two covalently bonded atoms. Can you repeat that? Half of the internuclear distance, half of the internuclear distance between two covalently bonded atoms. Half of the internuclear distance between two covalently bonded atoms is said to be its covalent radius. So this radius is also called as covalent radius. For suppose if it is 198 angstroms, suppose some rough value I am giving. If the internuclear distance is 198 angstroms between the nuclei of two chlorines, then half of this is 99 and 99, I think. Okay. So 99 is the covalent radius of first chlorine, 99 is that of second chlorine. This is how we can measure covalent radius. Once again, what's the definition of covalent radius? Half of the internuclear distance between two covalently bonded atoms is said to be its covalent radius. When it comes to this metallic radius, in a metal crystal, suppose metal atoms are existing like this side by side in this way. No overlapping exists, of course, no overlapping. Metal atoms are existing in a metal crystal, close or far, whatever it is. They exist at some distances. Then what we have to do in a given metal crystal, measure the internuclear distance of two adjacent metal atoms. Find the internuclear distance of two adjacent metal atoms, make it half. So what's this half is metallic radius of first metal atom, the other half is the metallic radius of second. So what's the definition we can give for metallic radius? Half of the internuclear distance. What is that? Half of the internuclear distance between two adjacent metal atoms in a metal crystal. Half of the internuclear distance between two adjacent metal atoms in its crystal lattice or in a metal crystal is said to be metallic radius. Okay, then the question is, among the covalent radius and metallic radius, whose value will be high? Whose value will be high? Usually for a same element, of course, for a same element, suppose you are measuring, suppose there is an element which can form covalent bond as well as which can exist in crystalline form. Then among covalent radius and metallic radius, whose value will be more? You can predict easily. In a covalent bond formation, there is an overlapping of atomic orbitals. You might have studied in lower classes, a bit introduction. But there is an overlapping. So they are more closer than they are actually. But in a metallic radius, there is no such overlapping. So relatively, here the internuclear distance is more. More the distance, more will be the radius on making it half. So we can say, or one can say, metallic radius is obviously greater than its covalent radius. So such a comparative study we have to make. Next is, when it comes to van der Waals radius, the next type of radius is van der Waals radius. You consider substance whose molecules were held by, consider a substance whose molecules were held by weak van der Waals forces. Suppose this is AB type of molecule. This is a molecule AB. Consider another molecule BC. Another molecule BC. In this molecule AB and BC were held by weak van der Waals forces of attraction. So if this molecule and this molecule were held by weak van der Waals forces of attraction, then radius measured with respect to such weak van der Waals force of attraction is called as van der Waals radius. Okay, suppose AB and BC were held by weak van der Waals forces in such a way, then measure the internuclear distance of this B and this B. Measure the internuclear distance and make it half. First half below is said to be van der Waals radius of this atom, the other half is said to be van der Waals radius of other atom. Okay, so what is van der Waals radius definition? Half of the internuclear distance of two atoms of different molecules. I am repeating, half of the internuclear distance between two atoms of different molecules that were held by weak van der Waals forces. I am repeating the definition. Half of the internuclear distance between two atoms of different molecules held by weak van der Waals forces is said to be its van der Waals radius. Obviously, among van der Waals radius and covalent radius and metallic radius, whose value will be higher if they are measured for the same element? So obviously we can say here they are more separated from one another. So van der Waals radius is much greater than metallic radius, which is greater than covalent radius. Metallic radius is also called as crystal radius. Okay, so both are same. In some books they may give the same as crystal radius, so they are same. Do remember that point. Next, so our next type of radius is ionic radius. Ionic radius means for what type of ion it is? It is of two types again: cationic radius, cation radius, and anion radius. Cation radius and anion radius. Cation radius means, suppose you consider an atom. You consider an atom. So where some n positive particles are there outside n negative electrons are there. It is neutral atom. Now from this neutral atom, if you remove an electron, inside the nucleus same n number of positive particles are there, but outside n minus 1 number of electrons. One electron is less. So nuclear charge is dominating. Nuclear charge is dominating. So the dominating nuclear charge attracts the less numbered outer electrons now, and as they are less in number, they will be held strongly to the nucleus. They come closer. When electrons comes closer, that itself is the size, no? Distance between the center of the nucleus and the outermost electron of the diffused electron cloud. So when electrons comes closer, we can say atomic size of the ion decreased. So this is said to be a cation whose radius is obviously smaller than its parent atom. Okay, so size of a cation is smaller than size of its neutral atom. Size of a cation is smaller than size of its neutral atom. When it comes to anion, suppose if you add an electron, inside nuclear charge will be as it is again, but outside number of electrons are n plus 1. Electronic charge is more. And due to repulsion, when electrons are more, there exists repulsion, and to minimize the repulsion, they have to move away. Electron cloud will be diffused away from the nucleus, and thus the size of the anion will be definitely larger than its parent neutral atom. So less numbered nuclear charge cannot attract the more numbered electrons. Thus electron density is diffused away from the nucleus, and size will be greater than its parent neutral atom. This size of anion is obviously greater than the size of its parent atom. So this is how cationic radius and anionic radius can be discussed. Then how to measure, how to find out this cationic and anionic radius from their interionic distances between cation and anion in ionic crystals. Interionic distances between cation and anion in ionic crystals, we can find out the cation radius as well as anion radius. This is about the types of radius. Okay, and already we discussed the 4 types of radius. What are they? Covalent radius, metallic or crystal radius, and van der Waals radius, and yes, ionic radius. Now let's discuss about the variation of this atomic radius across a period in the periodic table down the group in the periodic table. Now, in this aspect, means for studying the variation or trend of atomic radii, we have to study two terms here, shielding effect and effective nuclear charge. Shielding effect means the effect or shielding effect, also called as stopping effect. Stopping effect. Suppose this is a nucleus, it has some certain amount of positive charge with respect to number of protons. Around this, in definite shells, electrons were distributed. Okay. Now the question is, when the number of inner electrons are more, suppose this is first shell, second shell, third shell and fourth shell. First shell can accommodate 2 into 1 square, second shell can accommodate 2 into 2 square, means 8, third shell can accommodate 2 into 3 square, 18, fourth shell can accommodate 2 into 4 square, 32. We studied this in atomic structure. Suppose an electron entered here just now. There is only one electron in this fourth shell. For example, you consider. Now the question is how much 18 plus 10, 28 plus 1, 29 positive charges were there in the nucleus. Outside 10 plus 18, 28 plus 1, 29 electronic charges were there. My question is the same nuclear charge which is acting on this first electron can attract this 29th electron also? I am repeating the question. With what amount of nuclear attraction this nucleus is attracting these two electrons? With the same amount of nuclear force, can it attract this 29th electron? That's a question. Definitely not. Why? Because here this is the first shell electrons. Between nucleus and this first shell electrons, there is no other thing existing. So whatever the nuclear influence is there, it will completely act on these two electrons. In fact, the attraction on the first electron can be relatively shielded by second electron. That is also possible. A bit closer, relatively a small amount can be shielded. Similarly, when it comes to the next shell electron, the total nuclear attraction cannot be shown on these 8 electrons. A fraction will be shielded by the inner electrons. That effect is called a shielding effect. The phenomena of a stopping or reducing of nuclear attraction by the inner electrons is called as shielding effect. Like this, when it comes to these 18 electrons, 29 out of 29 may not reach these 18 electrons because a fraction may be shielded by these inner electrons, a fraction may be shielded by some of these 18 electrons. Suppose if you consider 18th electron, a fraction of nuclear attraction can be shielded by the previous 17 electrons out of these 18. So in this way, the stopping effect shown by the inner electrons, stopping effect shown by the inner electrons on nuclear charge, to reach the particular electron is called a shielding effect or screening effect or stopping effect. Screening effect or stopping effect. See, now the question is, which orbitals have more such a screening effect? Among SPDF, the known 4 types of orbitals, which is 3-dimensionally situated completely, s orbital is 100% spherical, right? It is spherical, 3-dimensionally arranged, it is symmetric with respect to all axes, right? That's why an s orbital can shield more and more effectively because it can move in any direction. It is spherical, s orbital is spherical. That's why the shielding effect of s orbital or s electron is greater than p, greater than d, greater than f. Because the p can shield either along x-axis or y-axis or z-axis. Whereas similarly d orbital, because of relatively complex shape, its shielding effect is still less than p. And when it comes to f orbital, already we discussed about its shape. It has 4-fold dumbbell, very complex shape. Because of complex dispersed shape of f orbital, its screening effect or shielding effect is very, very less. So what is the shielding effect order of orbitals? S orbital or s electron can shield more effectively than p, than d, than f. This is about a shielding effect. And one more point is, more the number of inner shells and inner shells with electrons, more will be the shielding effect shown on outer electrons. This is about a shielding effect. And when it comes to the next definition, that is effective nuclear charge. Sir, we have studied about nuclear charge. What is effective nuclear charge? what is effective nuclear charge? Effective nuclear charge. Actually, this concept is more important for competitive exams. Even its calculation also there for competitive exams for JEE mains and advanced, even for NEET also. We will discuss that in the competitive objective sessions. This is all PU sessions, right? So still we will discuss the definition part of this effective nuclear charge. Let us take the same example. Suppose 29 positive particles were there in a given atom. The first shell has 2, second shell has 8, third shell has 18, fourth shell has 1 electron suppose. Now, a fraction of this nuclear charge will be stopped by these 2 and these 8. Another fraction is stopped by these 18. After getting stopped by these inner shells with respect to their shielding effectability, rest of the nuclear charge, whichever is reaching practically on a particular electron, is said to be its effective nuclear charge. Means the fraction of nuclear charge that is actually reaching a particular electron to attract. Fraction of nuclear charge that is actually reaching a particular electron to attract that is said to be its effective nuclear charge. Effective nuclear charge of that particular electron. After getting shielded by all the inner electrons and the same shell electrons, if any, what fraction is actually reaching a given electron to hold it, okay, is said to be effective nuclear charge of that particular electron. Understood? So now, with respect to this effective nuclear charge, we have to study the variation of atomic radius across a period and down the group. See, trends of atomic radius. Trends of atomic radius. Now, firstly we will study across a period. Across a period. Suppose you consider second period elements, lithium. Lithium. Configuration is a 1s2. Atomic number is 3, right? It is 2s1. 1s2, 2s1. So the electron is at a distance of second shell from the nucleus. When it comes to beryllium, 1s2, 2s2. So one electron is increased. Here one proton is increased in the nucleus, one electron is increased outside the nucleus. There is an increase in positive charge as well as a negative charge, but distance between them is not increasing. So obviously what happens? Charges are increasing. Obviously their attraction increases, but the distance is not increasing. So attraction will be more and more, because of which these electrons comes relatively closer to the nucleus than lithium. So from lithium to beryllium, the effective nuclear charge, whatever the definition we discussed about effective nuclear charge, the fraction of nuclear charge that is actually acting on a particular electron, as distance is not increasing, not varying from lithium to beryllium, the effective nuclear charge will be more, because within the same distance more nuclear charge is existing, more electronic charges are existing, they will attract one another and they come closer. Electrons comes closer. So when electrons comes closer, obviously we can say the size is decreased. When it comes from beryllium to boron, electronic configuration is boron 5, atomic number 1s2, 2s2 and 2p1. See, again within the same distance, one positive charge is increased and one electronic negative charge is increased, but the distance between them is not varying. So because of this increase in nuclear attraction, again these electrons were more strongly held to the nucleus and they come closer and thus shows further decrease in size. Because from beryllium to boron, we can say effective nuclear charge is again increased. Effective nuclear charge is again increased. So across a period with increase in atomic number from one element to next element, what's happening? There is an increase in effective nuclear charge, which is given with the symbol Z effective. Due to increase in effective nuclear charge, atomic radius decreases from left to right across a period. So how do you explain the variation of atomic radius across a period? Due to increase in effective nuclear charge, with increase in atomic number, due to increase in effective nuclear charge, atomic radius decreases from left to right. So in this way, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So in this sense, we can say in a given period, suppose second period is considered, lithium is the one with larger size, fluorine is the one with smaller size. You may ask, sir, what about neon? Neon is radius is non-bonding radius in which atoms are far from one another. Whereas lithium to fluorine, the atoms are bonding radius. They are more closer than they are actually. So bonding radius we cannot compare with non-bonding radius. Okay. So inert gases like neon, their radius is non-bonding radius, which can be compared with van der Waals radius. Even on this comparison also, inert gases possess larger radius value than these. Of course, from fluorine to neon, there is an increase in atomic radius noticed because the inert gases were observed to be showing non-bonding radius. Understood? So in this way, across a period, with increase in atomic number, due to increase in effective nuclear charge, atomic radius decreases from left to right. Why effective nuclear charge increases? Tell me. With increase in atomic number, the distance between the increased positive and increased negative charge is not varying. So they come closer and held together to the nucleus. Electrons comes closer and held together more strongly. So atomic radius decreases. The same thing across a group or down the group. Instead of across a group, better we use down the group. How this atomic radii varies down the group. Suppose you start with the same lithium. Lithium electronic configuration is 1s2, 2s1. So between 2s1 and the nucleus, only 2 electrons are there. When it comes to sodium 11, 1s2, 2s2, 2p6 and 3s1. So this is first shell, this is second shell, this is third shell. This is first and second shell. Now you see, in case of lithium, inner electrons are only 2. But in case of sodium, between 3s1 and nucleus, 2 shells were there. A new shell is being added with 8 electrons. Obviously, shielding effect shown by 2 electrons is obviously greater than shielding effect shown by 10 electrons. As the shielding effect increases, electrons move to minimize the repulsion. As the electrons were not attracted strongly, electron cloud will be diffused away. With increase in atomic number down the group, as a new shell is being added, atomic size increases. Potassium 19, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So between 4s and nucleus, 1, 2, 3, another new shell is being added. Like this, with increase in atomic number down the group, with increase in atomic number, what is atomic number symbol? Z. With increase in atomic number, as a new shell is being added, atomic radius increases from top to bottom. So in any period, usually in any period except boron family, in any period, atomic size increases gradually. Boron family, not in opposite way, there is a slight variation because of the effect shown by transition elements. Okay, so in most of the groups down the group, atomic radius continuously increases as a new shell is being added with increase in atomic number. Actually, we have to discuss variation of atomic radius in transition elements and inner transition elements also, but for PU session, this is enough as per NCERT, but for objective sessions, those points we have to discuss. So, like variation of atomic radius in transition elements, in inner transition elements, how the atomic radius is varying, will they follow the same trend or any other trend is there? Similarly, in transition elements, down the group, atomic size is increasing in the same manner of other groups or any variation is there. These all points are important and comes in objective teaching, like level 2 teaching means for JEE, NEET and advanced. So in those sessions we will discuss about the variation of atomic radius in transition elements and inner transition elements. So once again, atomic radius across a period decreases from left to right due to increase in effective nuclear charge. This is the word you have to present. And down the group, atomic radius increases with increase in atomic number because a new shell is being added, right?